All right, so today we're going to be looking at section 7.8, which is improper integrals. We're going to cover the first half of it, which is improper integrals with infinite limits of integration. So it says, list two properties that make an integral an improper integral. So the first property is that either one or both of the limits of integration, so either a or b, the top or bottom, are infinite. So they're either going to infinity or negative infinity. Or the second criteria that can make it an improper integral is that f has a finite number of infinite discontinuities in the interval. Or in other words, that f is not continuous at some point in the interval a finite number of times. For the next piece, if an integrand has an infinite discontinuity, then, like I said in yesterday's video, I'm not quite sure what that fill-in is yet, so we can leave that fill-in blank for right now. For this piece, it says complete the following statements about improper integrals having infinite limits of integration. For the first one, it's kind of hard to read on your paper, but this says from a to infinity. So the integral from a to infinity of f of x dx equals the limit as b goes to infinity of a to b. So essentially you're just replacing that infinity with a b and taking the limit of the integral. So the limit as b approaches infinity from a to b of the function f of x dx. Vice versa, if the bottom is negative infinity, we can replace that with an a and say the limit as a goes to negative infinity from a to b of f of x dx. And for the third one, if it's from negative infinity to positive infinity, the whole thing, we have to split the interval up over a nice number. Usually that nice number is probably going to be 0, but we can split it up over any number. And so we go from negative infinity to c for the interval, and then from c to infinity of the interval as well, where c is any real number. And we'll use the same rules for these ones as we did up above for the a and b. In the first two cases, so for number 1 and 2, if the limit exists, then the improper integral converges. So you'll get a number for it and it will converge. Otherwise, the improper integral diverges, and we'll talk about that in just a minute. In the third case, the integral on the left will diverge if either of the improper integrals, these two, on the right diverges. So we'll have to look at each of those pieces individually. All right, the back of these notes we're actually going to look at tomorrow. So right now we're going to go open your book, and we're going to look at section 7.8. I'm looking at page 534. So if you want to look at page 534, we are doing example 1 right now. So let me put up a blank paper so we can write on that. All right, so the first example that we're going to be doing is the integral. We're going to evaluate the integral from 1 to infinity of dx over x. So, excuse me, this is the case where the upper limit goes to infinity, which is like case number 1. So I'm going to rewrite this. Instead of saying that the upper limit goes to infinity, I'm going to replace that with a b, and I'm going to say that the limit as b approaches infinity from 1 to infinity of this integral. I'm just going to rewrite it as 1 over x dx. That those two things are equal to each other or equivalent to each other. And now, oh, actually, I'm sorry. Let me fix this. This should be a b, not an infinity. There we go. And now I can take the integral of 1 over x. I know that the integral of 1 over x is ln of x. So I have the limit as b approaches infinity of ln of x from 1 to b. And if I use the fundamental theorem of calculus, I can plug in the b. So I have ln of b minus ln of 1 as f of b minus f of a. And the natural log of 1 is 0, so I just have the limit as b approaches infinity of ln of b minus 0, so I won't write that. Now if you plug infinity over here, you get ln of infinity. And the natural log of infinity is going to infinity, so this equals infinity. So the limit here does not exist. So if we look back at the front, it says if the improper integral diverges, it's because the limit does not exist. So the limit here doesn't exist, it goes to infinity. So this integral is actually going to diverge. We're not able to figure out how much area there is underneath it because it's an infinite amount of area from 1 to infinity. So that's example 1. Let's look at example 2 on that same page, 534. All right, so this is example A from number 2. the integral from 0 to infinity of e to the negative x dx. So again, I'm going to rewrite this with the limit. And since it's the upper integral going to infinity, it's going to be b going to infinity from 0 to b of e to the negative x dx. And I know what the integral of e to the negative x is. It's just negative e to the negative x. So I have the limit as b goes to infinity of negative e to the negative x from 0 to b. So if I use the fundamental theorem of calculus, I can plug in the b, I can plug in the 0, and I subtract them. So I have that f of b minus f of a looks like this. Now e to the 0 is just 1, so if I plug in the b, I get negative e to the negative infinity plus 1. Well, negative e to the negative infinity looks like this. I can do it as 1 over e to the positive infinity. So I have negative 1 over e to the positive infinity plus 1. Well, this piece here goes to 0 because 1 or negative 1 divided by a ginormous number is going to 0. So this is just 0 plus 1, which is 1. And then let's look at part B. All right, here's part B. Again, from 0 to infinity, I'm going to rewrite it with the limit of b going to infinity. From 0 to b, 1 over x squared plus 1 dx. All right, this is one of our integration rules that you guys should know already. When you have 1 over some... In the back of the book, actually, it's some constant squared plus or minus x squared. You have an integration rule. This is actually the arctangent. So the limit as b goes to infinity of tangent inverse, or arctangent, of x from 0 to b. Now the actual integral is like 1 over a times arctangent of x over a, but because a is 1, that's why I'm not writing all of those. All right, so from here, I'm plugging in the f of b minus f of a for the fundamental theorem of calculus. So I have tangent inverse of b minus tangent inverse of 0. And so if I plug in infinity to this, I get tangent inverse. Now it's the limit as it's going to infinity. So I can't actually plug in infinity, but I'm going to write it there just so that you guys can have an idea of what I'm talking about. Minus tangent inverse of 0. Now again, technically this is not correct. That's not going to be anything. It's the limit as it goes to infinity, not actually plugging in infinity. But we're going to look at the concept. So remember that arctangent, when we're looking at the unit circle, arctangent is the answer to what the original tangent was. So if tangent was some number, so for example, tangent of 0, if I'm putting tangents here, tangent of 0 would be 0 divided by 1, which is 0. Okay. Tangent of pi over 4 is radical 2 divided by 2, divided by, that's sine, divided by cosine, so radical 2 divided by 2, which is 1. And tangent of pi over 2 is 1 divided by 0, which is undefined. So if you're going tangent inverse, what you're given is these numbers. You're given tangent inverse of 0, tangent inverse of 1, tangent inverse of undefined, or 1 over 0, and you're going back to the angle. So for the first one, it would be 0. For the second one, it would be pi over 4. For the third one, it would be pi over 2. So if I'm looking over here, and I see that I have tangent inverse of 0, well, I know that tangent equals 0 at 0. So tangent inverse of 0 must equal 0. So that's minus 0. And for this one, I have tangent inverse of infinity. Well, infinity doesn't really make sense. You can't have infinity as an answer. But I'm trying to find out which number on the unit circle, or which angle on the unit circle, would produce a tangent value that's getting closer and closer and closer to infinity. You might be able to think of the graph. Remember that the graph goes to infinity, so you can think of which value that would be. But it actually ends up being pi over 2, Because if you think about this, 1 divided by 0, as 0, don't think of it as 0. Think of it as getting closer and closer and closer to pi over 2. The closer and closer you get to pi over 2, that closer and closer that number gets to 0 on the bottom. And so 1 divided by a really, 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 really small number is actually blowing up huge to infinity. So that's why tangent inverse of infinity actually equals pi over 2. Again, if you don't believe me from the unit circle, try looking at a graph of it, and you'll notice that at pi over 2, the graph of tangent is unbounded. It goes to infinity at that point. So this is just pi over 2 minus 0, which is pi over 2. Good. All right, here's another one. Now, as we get further into the book is assuming that you have learned everything previous to this, so they're assuming that you are kind of keeping pace with what we've been learning and always recalling on those things that we've been learning to apply them to new problems. Hence why the problems are in the order that they are in. So for this one, we need to find the integral of this. Obviously, we can rewrite it as the limit as b goes to infinity of this. But to take the integral of this, we are not quite able to take the integral very easily. There's no integration rules to help us with this one. So you may or may not recall, but I'll prompt your memory that we learned about integration by parts. So we're actually going to use integration by parts to solve this. So we need to know what u is, we need to know what dv is, and then we can go backwards to what du and v would be. So we're going to make dv be e to the negative x dx, and we'll make u be 1 minus x. So that if we take the derivative of u, we get du equals negative 1 dx, and we get that v equals negative e to the negative x as the integral of dv. So when we plug those into our integral, we have uv, which would be 1 minus x times negative e to the negative x. Oh, I'm sorry, just uv without an integral. Let me erase all that. It would just be uv, which is 1 minus x times negative e to the negative x minus the integral of v du. So negative e to the negative x times negative 1 dx. So that's what this integral up here equals. It'll be from 1 to infinity, but you get the point. So if I multiply over here, I get negative e to the negative x plus x e to the negative x. And then over here I have minus the integral of e to the negative x dx. So if I keep going with this, I have negative e to the negative x plus x e to the negative x minus the integral of e to the negative x is negative e to the negative x. So I actually get plus, or I'll do it here, negative e to the negative x. So this turns into a plus. And now this piece is going to cancel with this piece, plus c over here. And I just get x e to the negative x plus c. So that's the integration by parts of this. Now remember back to the beginning, we haven't actually done anything with our limit yet. So we haven't actually fixed anything with this 1 to infinity. So if I did it, the limit as b goes to infinity from 1 to b, that's what we're going to be doing now. So I'm going to take that into account now. So make sure you have all this written down. I'm going to erase some of it so we have some room. Alright, so here we go. So we have the limit as b goes to infinity of x e to the negative x from 1 to b. So that's where I got those limits of integration from. I'm bringing those back in now. So if I do my fundamental theorem of calculus, I get the limit as b goes to infinity of b e to the negative b minus 1 times e to the negative 1. So this is the limit as b goes to infinity. If I plug in infinity so far, I would get infinity times e to the negative infinity, which doesn't really help me out so much. The e to the negative 1, this piece here, just equals 1 over e. So we'll come back to that in just a minute. But over here I can rewrite this first part as the limit as b goes to infinity of b over e to the b minus 1 over e. We just said that was 1 over e. And now, if you remember from the last section, so far we've used integration by parts, which is a couple sections ago, and then the last section we just did was L'Hopital's rule. So if you plug in infinity here, you get infinity over infinity. which is the indeterminate form, which means we can use L'Hopital's rule. So if I take the derivative of the top and the derivative of the bottom, this will help me out, because now if I plug in infinity, I get 1 over e to the infinity power minus 1 over e. Well, e to the infinity is a huge number, so I have 1 divided by a huge number is 0. So that's 0 minus 1 over e. So the answer is just negative 1 over e. So we had to use 2 different rules from previous lessons in this one problem. So it's important to remember to keep thinking about those rules and to keep having them at the forefront of your mind to recall on them whenever you need them. All right, the last one we're going to look at is actually example number 4. All right, in this example, we have from negative infinity to positive infinity as our limits of integration. So this is the one that's like the third example that we actually have to split up into 2 separate integrals, one from negative infinity to c, and the other from c to positive infinity. And like I said earlier, c is probably going to be 0 because that's the easiest number to choose. So I'm going to separate this from negative infinity to 0 of e to the x over 1 plus e to the 2x dx, plus the integral from 0 to infinity of x e to the x over 1 plus e to the 2x dx. So once I do that, you may or may not recognize that this is actually one of the integration rules again. So this one is arctangent of e to the x. So we have the limit. For the first one, it's the limit as a goes to negative infinity. And then the integral of e to the x over 1 plus e to the 2x. Again, look in the back of the book or remind yourselves from those integration rules that this is tangent inverse of e to the x from, oops, this is not supposed to be to negative b. This should be to negative infinity, my bad. And this is from a to 0, plus the limit as b goes to positive infinity of tangent inverse of e to the x from 0 to b. So using the fundamental theorem of calculus twice, I have the limit as a goes to negative infinity of tangent inverse of 0, or e to the 0, I'm sorry, minus tangent inverse of e to the a plus the limit as b goes to infinity of tangent inverse of e to the b minus tangent inverse of e to the 0. So for this first piece, the limit as a goes to a negative infinity does not apply to this because it doesn't have any a's in it. So I can just evaluate tangent inverse of e to the 0 as is. So tangent inverse of e to the 0 is tangent inverse of 1. And if you go back to that unit circle that we just wrote down in the last problem, or actually 2 problems ago, I'm sorry, the unit circle said that tangent will equal 1 at pi over 4. So tangent inverse of tangent inverse of 1 equals pi over 4. So this first piece equals pi over 4 minus tangent inverse of e to the a. Well, if e to the a goes to negative infinity, that's like saying that you have tangent inverse of 1 over e to the positive infinity. And that's becoming a huge, 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 huge number again, remember? So, I'm sorry, I'm mistaken. It's not becoming a huge number. It's the opposite. The bottom is becoming a huge number. E to the infinity power is becoming a huge number, which means that 1 over that huge number is becoming 0. So this piece is actually tangent inverse of 0, which, again, if you look back 2 problems, is equal to 0. So far I have pi over 4 minus 0. Sorry, I'm not done with this line yet, so we're coming back to that one. I just wanted to make sure we were aware of that was 0. So now we're done with this piece here. And now we're done with this piece here. And we're moving on to the second half. So for the second half, it says the limit as b approaches infinity of tangent inverse of e to the b. So here's where it's becoming a huge number. E to the infinity power is huge, huge, huge. Remember from 2 problems ago that a huge, huge, huge number is getting closer and closer to 1 over 0. So that would be pi over 2. So this is plus pi over 2 minus tangent inverse of e to the 0. Remember we just talked about was pi over 4. So plus pi over 2 minus pi over 4. So if I add all this together, I get pi over 2. So that's the answer for the limit for the last one. All right, so that's it for today. I'll give you guys some homework problems. We'll finish the second half of this section at a later date.